So welcome back, Math 12, to section 7.3 on solving exponential equations. Today we're going to focus on three things. Determining the solution of exponential equations with bases that are powers of one another, like 5x is equal to 25 cubed. You notice that the 5 and the 25 are both powers of 5. We're going to look at solving problems that involve exponential growth or decay. And we're going to solve problems that apply exponential equations to situations involving loans, mortgages, and investments. Let's take a look at a first example. Sometimes it's important to rewrite one or both sides of an exponential equation so that they have the same base. So for example, let's say we've got 5x is equal to 25 cubed. What base might we use here if we wanted to rewrite both sides with the same base? Hopefully you're thinking 5. Which is great. So we rewrite this as 5 to the power of x is equal to 5 squared, which is 25, all cubed. And then using exponent laws, we could say that 5x is equal to 5 to the 2 times 3, or 5 to the 6. Well, if we've got an equation and the bases are the same on both sides of the equation, then it must also be true that the exponents are the same. So x must be equal to 6. And we've solved the exponential equation. So what about if we have something like 9 to the 2x is equal to 27 to the x plus 2? What bases might we use here? Well, we can't use 5, and 27 isn't a power of 9, but you might notice that both of them are powers of 3. So we could rewrite the 9 as 3 squared to the 2x and 3 cubed to the x plus 2. Well, again, using our exponent laws, we can clean that up a little bit and say that this becomes 3 to the 4x and 3 to the 3x plus 6. So if my bases are the same, then the exponents must be the same, and we're left with 4x is equal to 3x plus 6, or x is equal to 6. So let's rewrite each of the following expressions in bases of 2 or base 3. So we're going to have a, we're going to rewrite 27, we're going to rewrite 9 squared, 4 cubed, the cube root of 81 all squared. We'll do 1/8, and finally we'll take 8 to the 2/3 times the square root of 16 all cubed. So copy those, pause, and then come back and we'll check the solutions or how we rewrite those in either base 2 or base 3 as appropriate. Alright, so 27 I hope you recognize is a power of 3. So we can simply rewrite that as 3 cubed. No big deal. 9, I can't rewrite in base 2. I'm going to have to rewrite that in base 3. That's going to be 3 squared. But don't forget the 2 that's already out there. And using exponent laws, we multiply our powers here. We multiply the exponents to get 3 to the power of 4. 4, well, that can be rewritten as a base 3, so we'll have to use base 2. And in a similar way, that's going to be 2 squared to the power of 3, or 2 to the 6. The cube root of 81 squared. Well, there's a few exponent laws that we have to deal with here. First, let's just rewrite this as 81 to the 2/3, and then rewrite the 81 as a power of 3. So 81 is 3 times 3 is 9, 27, 81. So 81 is 3 to the power of 4, all to the power of 2/3. That means we get 3 to the 8/3. 1/8, that's 1 over 2 cubed, or 2 to the -3. And finally, the big daddy here, we've got 8 to the 2/3 and square root of 16 to the power of 3. So 8 to the 2/3 times 16 to the What would that be? 3 halves. Well, each of those is a power of 2, so that's like saying 2 cubed to the 2/3 times 2 to the 4 to the 3 halves. If we use our exponent laws, we'll get 2 squared times 2 to the 6. And we use exponent laws again, and when we multiply powers, we add the exponents, so we get 2 to the 8. Okay, replay it, listen to it again, make sure that you're clear on how to do each of those things because it becomes very important in what we do for solving equations in the next example. Okay, so now we can go on to example 2. And we can apply the techniques we learned in example 1 to solve equations by changing the base. So let's start with something like 4 to the x plus 2 is equal to 64 to the x. What base might we use to rewrite 4 and 64? Now, some of you might be thinking, well, 4 and 64, those are all powers of 2. Somebody else might be thinking, wait a minute, but they're both powers of 4 as well. And you're both right. In this case, we're going to use the 4 because it doesn't require us to do any changes over here on the left-hand side. So if we're using base 4, then we still have 4 to the x plus 2 over on the left, but when we rewrite the 64, we're going to rewrite it as 4 to the power of 3 raised to the power of x. Now, the power of power laws, the right-hand side becomes 4 to the 3x. And since the exponential equation is equal and the bases are equal, then we can make the exponents equal. We can equate the exponents and say that x plus 2 must be equal to 3x. Well, now it becomes like things that we've solved since grade 9. We can move the x over to the right side by subtracting x from both sides. We get 2 is equal to 2x. Divide both sides by 2, and we get x is equal to 1. Now, we can check our solutions by substituting into the left and right sides of the equation just to make sure that they're equal. So if we look at the left side, we can say that 4 to the 1 plus 2 is 4 to the power of 3, which we know is 64. On the right-hand side, we can say that 64 to the 1, well, that's also 64. So it must be true that the left side is equal to the right side, and that x is equal to 1 is our solution. Okay, well, we can do another. So let's try one this time with the base of, well, you tell me. Hopefully it's obvious already. If we've got 9 to the 4x is equal to 27 to the x minus 1, what base must we use? Well, you're right, it must be base 3. So we're going to use base 3. So that means that 9 gets rewritten as 3 squared to the 4x. 27 gets rewritten as 3 cubed to the x minus 1. Now remember our exponent laws, that if we have a power raised to another power, we multiply the exponents together. So that gives us 3 to the 8x is equal to 3, and careful here, this power multiplies the x and the 1 to get 3x minus 3. Since the bases are the same, we can equate the exponents, and we get 8x is equal to 3x minus 3. And if we subtract 3x from both sides, we get 5x equals negative 3, or x is equal to negative 3 over 5. On our left side, we've got 9 to the 4x, but the x has been replaced with negative 3/5. So that leaves us with 9 to the negative 12/5. On the right-hand side, we've got 27 to the negative 3/5 minus 1. That means 27 to the negative 8/5. And I don't know what the fifth root of those things are, so let's just plug that into our calculator. And both of those, it turns out, gives us 0.005126. So they must be the same. That means the left side equals the right side, and x must be equal to negative 3/5. Okay, so I want to give you a few more to do. Copy these down, pause the video, work them through, and then come back and check the video, and the solution will be here, and then we'll move on to example 3. And if you checked out the last question there, you'll notice that we get a solution of x equals 3, and that left side equals the right side. So yes, in fact, our solution is correct. In example 3, we're going to look at solving problems with different bases by systematic trial. So in this equation, or this question, Christina plans to buy a car. She's saved about $5,000, and the car costs $5,900. How long will she need to invest her money in a term deposit that pays 6.12% compounded quarterly before she has enough for the car? So in order to do this, we need to use the formula for compound interest. And that formula looks like this. A is equal to P times 1 plus I to the power of n. So in this particular case, our accumulated amount, the amount that she wants to have at the end, is the value of the car. So she wants to have $5,900. The amount that she invested, the principal, is the $5,000 that she had saved up until then. She's putting it into a term deposit. That's going to be the interest rate that she's going to earn, or the money she's going to earn. The multiplying factor is going to be 1 plus whatever the interest rate is per compounding period. That interest rate, expressed as a decimal, is 0.0612, 6.12%, and because it's compounding quarterly, we have to divide that interest rate, the rate she gets per year, by 4. And then that's going to be raised to the power of n, the total number of compounding periods, how long it takes for her to raise that kind of money. How long does it take to get to $5,900? So we can work with that. We're going to move the 5,000 over to the other side. So 5,900 divided by 5,000 is going to give us 1.18. And inside the brackets we can clean that up. 0.0612 divided by 4 is 0.0153. So we get 1.0153 to the power of n on the right hand side. Now we test different values of n until we get 1.18. So that's our systematic trial part. I don't have a way. I'm going to learn soon. In Chapter 8, in fact, we're going to learn how to do this quickly. But for now, we need to sort of guess and check. So I'm going to have 1.0153 to different values of n. I might try 5. That's going to give us 1.079. So that's a little bit too low. I could try 1.0153 to the power of 10. So that gives us, if we check that in our calculator, 1.164. That's too low, but it's a little closer. 1.0153 to the power of 15 comes in at 1.256. Yeah, that's too high. And we need to use a number that's closer to 10. So we'll try 11. To the power of 11 comes in at 1.182. Pretty close. In fact, close enough for us. So that means that it takes 11 compounding periods to reach our goal of $5,900. And since each of those compounding periods, since it was compounded quarterly, that meant there were 4 periods per year. So if I go 11 divided by 4, that means it's going to take 2.75 years to reach our goal. All right, so I'm going to give you another one to try. So the question is, how long does $1,000 need to be invested at 8.3% compounded semi-annually before it increases to $1,490? All right, good luck, and we'll see you in class tomorrow.